last lecture, we have talked about one-dimensional diffusion equation, how to non-dimensionalize the equation. Non-dimensionalization is an important operation that reduces the number of parameters. It also generalizes the problem quite a bit. Now, before we move into the numerical solution, first, we will conduct an analytical solution using separation of variable approach of this one-dimensional transient diffusion equation. Analytical solution is, of course, not part of this course, but if you understand how the analytical solution happens, it will give you a much deeper physical insight in the problem. And also, later on in this course, we will use this analytical solution as a benchmark. So when we will solve this problem numerically, are we doing the right thing? That validation we will ask from the analytical solution. If you feel this is too complicated for you, then you can skip the detail and go to the final part of this lecture, where you will see the expression and plot of the analytical solution. And we are going to use those expressions later on to match our numerical solution. So let us recall the governing equation, initial condition and boundary condition of our problem. Our problem is in dimensionless form. It goes in z direction between 0 and 1. The equation is del theta del tau is equal to del 2 theta del z2. The initial condition is theta equals 1. Boundary condition on both boundaries, theta equals 0. This type of boundary conditions where unknowns are specified at the boundaries, I know theta equals 0, theta equals 0 at boundary condition. These are called Dirichlet boundary condition. These are actually slightly easier compared to other type of boundary conditions. For example, if fluxes are specified, then that becomes Neumann type boundary conditions. We'll discuss it more later. But right now, let's see how we can solve this problem analytically. Analytical solution can be done in many ways, but here we will use separation of variable. Separation of variable assumes that theta, which is a function of tau and z, it is actually a product of some function of tau multiplied by some other function of z. In general, this cannot happen. This is a simplification that you see. So we have to first ask that when it will happen. Of course, a detailed discussion of separation of variable is not part of the course, but at least we have to see that under what condition we can assume this kind of a separable solution. The condition for having separable solution in transient case is like this. We must have a linear and homogeneous equation. We have already discussed what is linear and what is homogeneous. If you don't remember, you can go back to that lecture. So for separation of variable to be applicable, we need linear homogeneous equation and linear homogeneous boundary conditions. We need linear non-homogeneous initial condition. This condition, of course, they are true only for this transient case. For steady state case, it will be slightly different because there is no initial condition in steady state case. So we have to define it slightly differently, and we'll talk about it when situation comes. But first, let us see that are we satisfying this condition? Well, of course, this is a linear equation. If u is a solution of this equation and v is a solution of this equation, then u plus v will also be a solution of this equation. You can check that out by plugging u and v here. Similarly, if u is a solution of this equation, then some constant a times u will also be a solution of this equation. So this is indeed a linear equation. There is no constant hanging here, therefore it is homogeneous. Both the terms contain theta, so it is homogeneous. Now look at our boundary condition. They are of course linear as well as homogeneous because they are both 0. If theta equals 1 or 2 at boundary, then it becomes non-homogeneous, then we have a problem. We have to deal with it differently. So now we have linear homogeneous equation, linear homogeneous boundary condition. See, this theta equals 1 is of course a linear condition, and 1, because it is 1, this is non-homogeneous. It is homogeneous if it is 0, but it is non-homogeneous. So this is non-homogeneous initial condition. Think about if this is also homogeneous, then we have trivial solution theta equals 0. That will satisfy everything. But here we have linear homogeneous equation, linear homogeneous boundary conditions, and linear non-homogeneous initial conditions. So as I said that we'll go and solve this equation now because we see that all the conditions are satisfied. Now why this separation of variable type solution will appear, why these conditions are important, this type of detailed discussion of separation variable technique we will not do here. For that you have to go to a math book which discusses partial differential equation. Okay, so now with this separation of variable, what we can do is that this theta 1 is only a function of tau and theta 2 is only a function of z. So any derivative of theta 1 or theta 2, they are actually ordinary differential, they are not partial. So this ordinary derivatives, then it will give us our goal here to do it, that this partial differential equation we want to transform it to ordinary differential equation, because we know how to solve ordinary differential equation, that is much easier. Separation of variable will help us to transform this to ordinary differential equation. As we'll go for numerical solution, you will see that we'll transform this PDE to linear equations because we know how to solve linear equations numerically. So here we are going to transform this PDE to ODE, but how we are going to do that? So this theta is a function of theta 1 and theta 2. So now if I take the time derivative of theta, theta 2 is a function of z, so nothing happens there. It only takes the derivative of theta 1, and this is an usual derivative. This is not partial derivative. This is d theta 1 dt. Similarly, when I take the derivative with respect to z, then theta 1 is a function of tau only. So the derivative will only appear in theta 2, and theta 2 is a function of z only. Therefore, this derivative is a usual ordinary derivative, not partial derivative. So now I can plug this in my equation, these two results, and see how does it look like. So this governing equation now, it has transformed into theta 1 prime, theta 2, theta 1, theta 2 double prime. So first derivative of theta 1, and this is double derivative of theta 2, but they are ordinary derivative, not partial. That is the good thing. So now I take theta 1 and theta 2 on one side. So here we see that I have left hand side theta 1 prime by theta 1, both are function of tau only. Right hand side theta 2 double prime by theta 2, both are functions of z only. So a function of tau is equal to a function of z. That really cannot happen unless both of them are constant. So here we are taking this constant. Lambda we are taking constant. Also we are taking lambda as non-zero, because if it is 0 then theta 1 prime is 0. So it comes out to be an ordinary differential equation. Theta 2 prime will be 0. It will become a steady state solution. So we drop that. So this is a constant, but why we are taking negative? We are taking negative to make sure that this is a constant, but this is a negative constant. Lambda square is positive, so minus lambda square is negative. You will see later on only negative will give us meaningful results, positive will not. And we'll see quickly that why it is so. So now we have these two equations. Both you can see they are ordinary differential equations, not partial. So let's take up these two equations and solve them. Once we solve theta 1 and theta 2, we can simply plug it here and we'll get our solution theta, because that would be a product of theta 1 and theta 2. So this is a simple process now. So let's write this. This is 1 by theta 1 d theta 1 d tau. This is, as I said, ordinary differential equation. So I can take d tau on the right side. This is a usual solution procedure. This will give us log, and we can change that to exponential. So now I have brought a constant a1, and this is exponential minus lambda square tau. So theta 1 I have it. I have one constant there. Similarly, theta 2, if I take, theta 2 will take us to plus lambda square theta 2 here. And this is not tau, this would be z. And this lambda square theta 2, it will give us this theta 2 z is a2 sine lambda z plus a3 cos lambda z. This a2 and a3 are actually constants. So this is coming as sine and cos because lambda is positive. If it is negative, then it will come in exponential. So this d square plus lambda square is 0. So d is plus minus I. It is imaginary since lambda square is greater than 0. That is why it is coming out to be sine and cos. So this term is showing us the time variation, how this solution will vary in time, because lambda is positive minus lambda square is negative. We can see that with time this term will actually diminish. Only this theta 2 will prevail, and that is what is something physical, that we know that with time it will reach to another steady state solution. So the time dependent term should actually go down. That is why taking this as minus lambda square here makes sense. All right, so let's move forward. So now we have our separation of variable theta, which is a product of theta 1 and theta 2. We have derived theta 1 and theta 2 here. So all we have to do it now just to multiply and finding the constant, and that's it is actually, it's as simple as that. If I multiply, then I have this theta and I take this a1 exponential lambda square tau here multiplied by this theta 2, that is sine plus cos. So I have three constants here, but why take three constants? I mean, we can multiply a1, a2 and a1, a3, and that way we get two constants. That is much better. So that's how we write it. I have theta is exponential minus lambda square tau. I have a sine lambda z, b cos lambda z. This a1, a2 and a1, a2 is a and b respectively. As time progresses, this exponential minus lambda square tau will go to 0, and I can have a steady state solution that will come from this sine plus cos. So it looks pretty good now. So all we have to do is now we have to find out a, b, and also this lambda we don't know. So we have these unknowns, and we have to use these initial conditions, boundary conditions, to figure them out, and then the solution will be done. So great, let's see how we can do so. So we have two boundary conditions, and let's start from there. So first boundary condition is this z equals 0, theta is 0. This is my expression of theta. This is 0. My z equals 0, so exponential terms nothing happens. Z equals 0 gives this is 0 and this is 1 for z equals 0. That means this is 0, so a goes out, only b remains. Cos lambda z is 1. So b exponential minus lambda square tau is 0. This can only happen with b equals 0. Therefore, we have simplified the problem. One term is going out. So our theta gives us this a exponential minus lambda square tau sine lambda z. You can see very clearly that this is a constant multiplied by a function of tau multiplied by a function of z. So theta tau z is a exponential minus lambda square tau sine lambda z. As tau tends to infinity, this exponential term goes towards 0 and theta becomes 0, and that's what we are expecting, that as infinite time, this non-dimensional temperature will come down to 0. Now look at the other part here. Here this theta as z equals 1 is 0. So now I take this expression, not the previous one, because I have simplified it. I take this expression and I plug in 0 here, a exponential minus lambda square tau, nothing happens here. This becomes sine lambda because z is 1. Now for this to become 0, of course, a cannot be 0, because if a is 0, then the entire theta is 0 and nothing happens. We don't get any solution. This exponential term is non-zero, so this sine lambda should be 0. But sine lambda 0, with this condition we have a problem, because then we can have many different lambda for which sine lambda will be 0. In fact, we can have lambda equals n pi, where n is 0, plus minus 1, plus minus 2, etc., etc. For each of these solutions, sine lambda will be 0. So this is a problem now, and what we are going to do, we have to see that. But we can write this as n square pi square or n pi z, but it doesn't solve our problem because we have so many solutions. Every n gives us a solution of this equation. Each of this n, 0 to infinity, will give us solution. So now let us see that what we are going to do about it. Each value of lambda, this, or each value of n, lambda is n pi, will give us a solution. So I write this, each solution is theta n is a exponential minus lambda n squared tau sine lambda n z. So this lambda n means n pi for n equals 0, plus minus 1, plus minus 2, etc. Each of this is a solution. Now we know that this equation is a linear equation. So in a linear equation, if theta 1 is a solution, theta 2 is a solution, then theta 1 plus theta 2 is a solution, some constant multiplied by theta 1 is a solution. So in general, some constant multiplied by theta 1 plus some constant multiplied by theta 2 should be a solution of this equation if theta 1 and theta 2 are solution. So this is something we call linear superposition, which tells us that because each of these solution, they satisfy this equation, a linear combination of them will satisfy the equation. So for certain Cn's are constant. For this constant, I can take a linear combination of them. For this arbitrary constant Cn's, that would be a solution theta. Our solution should come like this. Now it complicates the problem now. What we are going to do about it, let us see. Now we take some particular case. Let us say for n equals 0. So what happens at n equals 0? For n equals 0, lambda is 0, sine is 0. So this is a series actually. This is an infinite series. So in this infinite series, the n equals 0 term doesn't contribute anything because it terms this theta n will be 0. For n equals 0, lambda will be 0. So that doesn't contribute anything. What happens for n equals 1? So for n equals plus or minus 1, so if it is plus 1, then it is sine, simply n equals 1. So this is pi, lambda is pi. So for plus 1, this will be pi z. For minus 1, this would be minus pi z. So that can come out. So here this is sine pi z. Minus sine pi z is minus will come out. So whatever the solution that comes at n equals minus 1, that will be minus of n equals 1 solution for this theta n. So what I can do, because this series had all the terms plus 1 and minus 1, I can club some of this term. Because minus 1 is simply minus of plus 1. So let us see how I can club it. So for example, Cn equals 1. and theta n equals 1 plus c n equals minus 1 theta n equals minus 1, this kind of series it is. Now I can take this c n equals 1 minus c n equals minus 1 and theta n equals 1. So theta n equals minus 1 I can remove because it is negative of theta n equals 1. So I can cut out half of this n's actually. But now my constant has changed. It is now c. So I give a new name. This is d n equals 1, theta n equals 1, tau z. Which tells me that if I take this d theta, then I don't have to take care of this plus and minus. I can only go with the pluses. That is the advantage of using this. Therefore, 0 I have removed. I am not taking 0. 1 I have seen that this happens. Minus 1 and plus 1 I can club them together. The same thing I should be able to do for 2, 3, 4, etc. etc. Therefore, this series now with this new constant d, it comes from 1 to infinity. So 1, 2, 3, etc. etc. infinity. 0 is not there. Negatives are out. So we have simplified a bit, but it's not enough yet because we don't know the d's. So here we are. I can plug it in with this exponential n square pi square and sine n pi z from this lambda equals n pi. And here I had this in theta n, I had this a, and here I have dn. So clubbing this a and dn, I write simply an. I don't want to keep two constant. This is just one constant. So now you see the problem now. The problem is now that theta is a linear combination of all this, but all these an's I have to find out. How many? Well, infinite number of an's I have to find out. For that I need infinite number of condition, but I don't have infinite number of condition. The only thing that I have is the initial condition now, and I have to evaluate this an. For 0 I can cut from 1, 2, 3 up to infinity. So what do I do? So I apply this initial condition. As I apply this, my initial condition was tau equals 0, theta is 1. So I have 1, tau equals 0 gives this exponential equals 1 for tau equals 0. So which means this is 1 is equal to sum of n equals 1 to infinity an sine n pi z. So this is the only equation I have, and I have to figure out infinite number of an from here. This looks pretty impossible, but you will see that there is a clever way of actually doing it. So let's pause here and go back to some of this very simple trigonometric relation that you have learned in your high school. You have learned this sine A, sine B formula in high school from trigonometry. So I have this sine m pi z, sine n pi z. If I break them, I'll get half of cos m pi z minus n pi z minus cos m pi z plus n pi z, where m and n are integers. This is from your high school days, this is a trigonometric identity. Now, if I integrate this both sides, then what happens is that I am integrating each of this term. So cos m minus n pi z dz we can integrate is very easily. It's not a problem. So I integrate, and as I integrate, I see that it is sine m minus n pi z to m minus n, sine m plus n, etc. etc. This looks nice, but it creates a problem. If m equals n, then this term will create a problem. So I have to do something about this term, and this expression is valid only when m is not equal to n. Otherwise, this will give a problem. For m equal to n, what happens that this cos m minus n pi z, here m minus n becomes 0. That means this cos term becomes 1. This is only integration of dz. That means its value will be simply z. So for m equals n, the second term, nothing changes in second term, but the first term is this z by 2 for m equals n. Why is it important? So let's hold on and go a little farther. So we have seen this relation of integration of sine m pi z n pi z, and it gives us two expressions for m equals n, m equals n. Here m, n are positive integers. Now this integral, if I take the limit between 0 and 1, what happens? Now you can see that if I take it is between 0 and 1, what happens here is that for m not equals n, I have here, this is sine m minus n pi z, sine m plus n pi z, but all sine pi for any k, this sine k pi will be 0. Sine pi, sine 2 pi, sine 3 pi, etc., all are 0. Therefore, both these terms will be 0. Therefore, if I integrate here, that would be 0 for m not equal to n. And also for m equals n, the second term will be 0, but first term will remain. Therefore, this will be 1 by 2 for m equals n. Now, we are going to use this idea here to evaluate our ANs. So now we come back to this expression, and in this expression, I multiply both sides with sine m pi z. So this side is an sine n pi z into m pi z summation. This side I had 1, therefore it is sine m pi z, and now I integrate between 0 to 1. So what happens on the right hand side, we have to look for it, but what happens on the left hand side? See, in the left hand side, if m and n are not equal, then this will go away, there will be simply 0. But if m and n are equal, this will be 1 by 2. Which means that in this series, n goes from 1 to infinity. So when I integrate this, I am integrating these infinite terms in a series, each term in a series. But only one term will give me non-zero value, where this m and n will match. All other terms m and n will not match, and therefore all of them will be 0. The term for will m and n match, so that is the m equals n case, and in m equals n case, this is 1 by 2. So all are 0 is except m equals n, and for m equals n, this is simply 1 by 2 an. On the other side, because m equals n, I can simply write n here, m equals n. I have to evaluate this, I don't know what will happen here. So let's evaluate. This is a simple integral. If I evaluate, I guess this cos n pi z, and between 0 to 1 and n pi. So this is simple. This is cos n pi can go either plus 1 or minus 1, and cos 0 can go only 1. So this comes as n, this 2 comes this side. This is the cos n pi, that is minus 1 to the power n, and this is 1 from cos 0 divided by n pi. This will be valid for n equals 1, 2, etc. Now we are ready to close this. Now you see this an, I have this theta and I have this expression of an. Now look at this. N goes from 1 to infinity. This is an infinite series, and I have the values for an. What happens for n equals 1? For n equals 1, this is 1. This is negative 1, negative 1, negative, positive. So this will be 4 by n pi or 4 by pi. What happens for n equals 2? Minus 1 to the power 2 becomes 1, 1 minus 1, 0. Which tells us that this n will be 0 if n is even, but n will be non-zero, which means 4 by n pi when n is odd. So even in this series, we can actually cut out some of the terms. We don't have to take all. We can take only odd n's in this series, and that gives us the solution of the diffusion equation. That is 4 by pi. This 4 by pi is coming out, and this 1 by n is this 4 by n pi is my an. So 4 by pi is there, 1 by n should be there because we are summing over n. This exponential term is here, sine n pi z is here. So now we have the solution. It looks like pretty complicated, but this is a solution in infinite series. This is not a closed form, but we can truncate the series after some term and we'll get a reasonable solution. This is of course dimensionless form. If you want to take in dimensional form, then theta we know t minus t1 by t2 minus t1, tau is alpha t by L square, and z is x by L. How does this solution look like? Well, you can plot this. Once you plot this, it will look like this. This is the initial condition. Initial condition means tau equals 0. Here theta equals 1. And then both ends suddenly comes at 0 temperature. The inside slowly comes down. So if you take any particular z location here, let's say this one, initially it was 1 and then it slowly temperature drops up to the steady state. This is the solution where everything is 0. So this is the initial solution, everything 1, to the final steady state, everything is 0, and in between you will get family of lines like this. These are the temperature profile in the rod. To summarize, we have used the separation of variable technique. This is an important technique, but if you have a problem in understanding what we did, you can skip this, but remember the last part. That will be useful. We will keep on using this. The solution, the expression, you try to understand this, try to understand it physically, that what is happening. The separation of variable technique is an important technique in analytical solution of partial differential equation. Not only in this equation, there are many other linear partial differential equations we solve using separation of variables. So if you can understand this and learn this, this will go a long way for all engineers and scientists. For your exercise, you use the equation we have derived at the end, and as z equals 0.5, how the theta changes in dimensionless time, you plot that. Using any software, it could be Python or MATLAB or any other software, even maybe Excel. So that's all for this lecture. Thank you, and I'll see you in next class.